Hello, everyone, and welcome to my session about dynamic language performance in this new invoked dynamic world in which we're living as bytecode on the JVM. So the thing we need to answer with this session is the stuff that Attila and I mostly have been working on in the dynamic languages part of the Java language team the last year or so, is how far invoked dynamic takes us towards real native runtime-like performance for a dynamic language. We work a lot on the Nashorn project, which is JavaScript, but this is a more generic problem than that. So I'm happy to say that after a few years of stumbling in darkness and a lot of work from the JIT team and from us, we've actually been able to answer this question with pretty far, actually, and I'll try to explain why. How many in here actually saw my talk at last year's JVMLS? Yeah, it's a fair part of the crowd. That's good, because then I sort of explained what we were about to do, and now we spent the last 9 or 10 months doing it with some very interesting and nice results. This is the legal slide, because it's okay. It's very good that I have it here, because I'm going to talk about the future, and this Oracle's legal slide says basically anything Marcus tells you about the future might be a lie and not happen. So most of you probably know me. I'm gradually turning into more and more of a hipster the more I work with dynamic languages. If you want to know about invoked dynamic performance, dynamic language performance on the JVM, the Nashorn project, and things like that, you're free to follow me on Twitter. I tweet a lot. I curse a lot about JavaScript. Most of you probably know about the Nashorn JavaScript runtime already, which is a very quick intro. And then I'll delve into what Attila and I have been up to, show you the performance we got for JavaScript as bytecode on the JVM and tell you how we did it. And then I'll talk about the future, where we're going to bring this architecture next. So Nashorn, as you probably know, is a JavaScript runtime, 100% JavaScript, ECMA compliant runtime written in Java. It's part of JDK 8, and it's based on invoked dynamic. Everything in JavaScript, such as calls or getters or setters, are implemented with invoked dynamic bytecodes in the bytecode that Nashorn generates. We don't do any interpretation or anything. We JIT everything to bytecode right now, and that may or may not be a good idea. I'll talk about warm-up during this talk. We have some limited ECMA 6 support coming out in JDK 8240, such as the let and const keyword. I'm not sure how many of you have played with Nashorn at all in this room, and yeah, there's still a fair crowd. So this is like a good audience for this talk, I think. So Java 8 was the first version for public consumption. Java 8220, which was originally where our performance work was targeted, has security fixes and several JIT and JDK improvements to invoke dynamic. We spent a lot of time with the JIT team, and most of the stuff that we've done together throughout the winter to the JIT has gotten into 8220 already, which is very good. 8240 will be a performance release where we put in the Nashorn with the new execution architecture with these wonderful things that I will show you shortly that we developed the last year. And then Java 9 will contain various, that's the future, so who knows, right? But hopefully we'll turn this into a more mature runtime architecture. Hopefully we'll have things like Java Flight Recorder integration and things, but I can't promise anything, and I have a disclaimer saying I don't need to. So all the performance things I'll talk about today will go into 8240. So 99% to 100% of what you see in these slides will be in 8240, which I think is due to be released at New Year's. I might be wrong, but I think New Year's is the release date. So the evangelist blurb that you see from the PMs out in the field right now about Nashorn is that it's the Rhino replacement. It's a really fast, 100% JavaScript compliant, invoked dynamic based runtime for JavaScript written in Java, runs on top of the JVM. The evangelist blurb that I would like to see, and I think we're moving towards, given this work that I've been doing, is something like Nashorn is a runtime for dynamic languages on the JVM. It takes away the pain and performance loss of bridging the gap between language and bytecode. Types, objects, and code are automatically adapted to be an optimal fit in the JVM mold. This sounds quite fuzzy, but this is going from a specific invoked dynamic-based JavaScript runtime to a dynamic language execution architecture. And the more we work on it, the more things like this fall out naturally, which is quite exciting.
Kind of a dynamic language runtime of sorts?
Yes, kind of a dynamic language toolkit runtime. Yeah, whatever. So we all know about JavaScript, which is currently taking over the world. It's dangerous, and it's not really pretty, and it tends to stick together just long enough for the developer to either ship or hurt himself. So the interesting thing about JavaScript is that it's both very dynamic and has so many quirks related to dynamic languages that if you get to run JavaScript efficiently, you have solved a lot of generic dynamic language problems for other languages at the same time. And that's it. I mean, once you're immune to the terrible, you're free. Then you're not afraid to open any door because it can't get worse. So this is what Jerry has. I mean, hi Jerry. This is one of the best quotes about what it's like to be a developer. And by God, have we waited in the terrible this last year? But we're not really scared anymore. We just open new doors and we get hit by stuff in the head. And we've solved so many JavaScript problems. So we start seeing patterns everywhere. So, invoke dynamic performance. This is Java 8, the stuff that we ship with Nashorn. This is the Octane benchmark, which is pretty much the spec JVM 98 of the JavaScript world, so it should be taken with a grain of salt. The red bars is what Nashorn in JDK 8 does. I've normalized them to 1. And the blue bars is Rhino, which was the previous JavaScript runtime written in Java that existed. So already, when we released the first Nashorn version, we pretty much beat Rhino on everything, not by a comfortable factor of 10, but on everything. And there are some blue bars missing, which basically Rhino crashes on these benchmarks, or it doesn't run them, or doesn't support the APIs to run them. So where are we today? These last 9 months, what have we done? I'll add some green bars, still normalizing on the red bars. This is where we are today. And it's quite amazing, actually, because, I mean, we've done a lot of work. A lot of the work we've done has been to create an architecture so we could build the optimizations. And a lot of this came in for free with the architecture. And only part of it is like directed efforts to optimize JavaScript. So we haven't concentrated on 100% performance work. A lot of it was trial and error developing a runtime architecture for Nashorn. So the stuff that starts to fall out here is just the beginning of what we can achieve. So let's look at V8, which is a native JavaScript runtime and extremely fast because it doesn't need to cater to bytecode or the JVM underneath it. We're in the ballpark. There are some things like the crypto number crunching benchmark where it's like a factor 2 faster, but otherwise you see that we are actually very close to V8 performance in many cases. There are ray traces crunching floating points. I'm quite happy with these things in just 9 months of effort once we got the architecture right. To be really fair and not to be accused of benchmarking number dishonesty, I'll show you the V8 bleeding edge bits, which I built Friday. They've done some improvements basically to ray trace. Otherwise, it's still pretty much in the same ballpark. And we also have stuff to do optimization-wise. But this is the first time that anyone has gotten close to like native JavaScript performance with something that runs on top of the JVM. And there's also Node, avatar.js, which is the Oracle project to run a Node-like server-side process. Project Avatar has a couple of benchmarks that they use for self-validation, the HTTP benchmark and the REST benchmark. And they are actually comparable to or better than V8, or rather Node, I should say, running the same benchmarks right now, which is quite impressive. And all this will go into 8U40. And you can already verify these things and play with this stuff yourself because all the code is open. Right now, some of the code sits in Java 9, JDK 9, and will be back merged. We also exposed some mechanisms, like explicit mechanisms that they can use through JavaScript and JSR 223, because you're allowed to cheat if you're running Java on top of the JavaScript on top of Java. Which is the attractive use case there. So it's been a frustrating year, but it's also been a very rewarding year in that we feel we are technically very much in the right direction, and we already started to get performance from this. So how did we do it? What is the secret sauce to this performance? The secret sauce is called optimistic type runtime architecture for dynamic languages. There's a JEP that's been finalized, or almost finalized. It's number 196 if you want to check out a description of the architecture in JEP form. So how did we think? The traditional mindset is that since the dawn of time, which is 1995, people have started to take their non-Java languages, try to compile them to bytecode and run them on the JVM. Of course you want to do that because you save so much complexity by having someone else do the memory management and the JIT optimizations for you. So people have sort of assumed that, the JVM contains so much goodies, and if we just create some kind of bytecode, all the magic in the JVM will optimize this extremely well, which is of course not true, because bytecode has some quirks. It's strongly typed. It's not sure that your language is strongly typed, so that's the main hurdle to come through. You need to create bytecode that the JVM can understand and use. And the other thing is that the JVM, the last 20 years, has been running mostly Java, so it's optimized to run Java-like bytecode and not any arbitrary bytecode. So once you realize this, there is no really good answer how to do this in bytecode, we realized. So we have to figure out a way to generate bytecode that the JVM, for dynamic languages, that the JVM will run as fast as Java bytecode. Invoke dynamic is, of course, one large key. Without that, you couldn't solve anything in the dynamic language space, but types is a very big problem as well. So consider the greatest common divisor function. It's virtually identical if you write it in Java. Right now, it's JavaScript. The only difference would be that you specialize the types of x and y, so x and y, so that they are that they're ints, probably, because that's what you would use it for. So it'd say int in front of the parameters and in front of the temporary variables a and b if this were Java. Otherwise, it's identical. In JavaScript, if your compiler only has this much, you can't prove what x and y are when you're statically compiling the code. So they may be doubles or strings or objects that have side effects when you coerce them to numbers. You know a few things conservatively in JavaScript, that subtraction has to be applied on arithmetic, is an arithmetic operation. So a and b are doubles or ints or longs or a numeric type, things like that, but you don't know much. So if you generate bytecode for the greatest common divisor to be JavaScript compliant, conservative, to make sure that it will always be semantically correct for all inputs, it looks something like this. Can you read this at all? It's not important to go into detail and see every bytecode I'll show you here. I'm mainly looking at code mass versus code mass, or at least that's my last-minute excuse for small fonts. So this is what JavaScript, greatest common divisor, would look like, using only what can be statically proven. Subtraction is a double instruction. It's conservatively right if you do a double, but local variables have to be represented as objects because you can't see what they are. And x and y can be anything. So we have to do JavaScript-specific coercion to number to do this subtraction. It's pretty horrible. If you compile the integer version written in Java, it's significantly shorter, contains no calls to anywhere, and it's basically a nice thin leaf method using only integer ops. And if you benchmark these against each other, the right one is about a factor 150 faster than the left one, where you have just enough to be conservatively correct for all inputs in JavaScript. So obviously the answer to get performance from the JVM is to generate Java-like bytecode. The bytecode layer are the round holes, and here I come with my red bar of JavaScript, and it doesn't really fit, which is true for many dynamic languages that don't have types. And of course, you can widen the hole a bit with things like invoke dynamic, or rather a lot, but you need to drill a better hole for all these typeless languages. And we think that the hole we drilled to solve the JavaScript problem for Nashorn, a lot of other good stuff fits into that hole. So we're glimpsing an architecture for dynamic languages to bytecode that's falling out here. So optimistic types, I talked about this in detail last year, but to recap, basically it works. You don't know all the types when you compile a method. You generate an optimistic as possible. If you see x and y, you assume them to be the narrowest type as possible, which would be ints, 32-bit ints. And then for every optimistic operation, such as like retrieving an int field from scope, it doesn't need to be an int, it could be a double, so it can fail. or doing an integer subtraction, it may overflow and the result may not fit in 32 bits, so it can fail. We call any such operation an optimistic operation and surround it with exception handlers. And when a type is too narrow, we throw an exception. The runtime system throws an exception, which we call an unwarranted optimism exception. We store the frame state from where the exception is thrown, take sort of a primitive mini continuation and finish the method. I'll show you a little bit about this in a minute. And we tell our linker to regenerate a more conservative method. If you have an integer subtraction like in GCD and suddenly you overflowed your 32 bits, an exception would be thrown and you generate a method where you use, say, a double for that type instead, or a long, or something that fits. Optimistic types, I mean, representing everything as object is the pessimistic way to do it. That was the first bytecode I showed you. We internally use int longs and doubles. We're thinking about adding booleans as an orthogonal path here to the narrower types and object that we use for type guesses in Nashorn. And of course, any type can turn into an arbitrary wider type depending on the result of a too pessimistic operation or too optimistic operation. To illustrate how this works really simply, I'll just look at a very small multiplication program in JavaScript. It multiplies x and y. X and y are variables that are in scope, which means that they're not declared in this function. They're in this function's scope. They exist somewhere else outside it. And in Java, to represent this in Java, they have to be in memory somewhere in a field or in an array and have to be read from memory to be accessible. The conservative Java bytecode for this method would basically consist of two invoke dynamic getters that get x and get y, queries the results to numbers. Note that they have the return type objects. We are conservative. We don't care what they are. If there are objects, we'll get back Java-lang integers. There'll still be objects. Then we turn them into numbers, which is more than, hopefully not more than just unboxing them, but in JavaScript, someone can have overridden the toNumber property and have global side effects or whatever, so you don't really know how complex toNumber is as well in this conservative world. You do the multiplication with a dmul, which is guaranteed to fit all JavaScript numbers, and at least you know the return value of the method is a double, so you can do a d-return. And let's forget about this. I mean, let's assume that we're dealing with ints. We don't see anything, but we assume it's ints, and then the bytecode will look something like this instead. You'll change the int-getter return types to ints for x and y. You won't do a dmul. We do an imul, which is an indie, because we have to check that the operation might not overflow. The multiplication can be wider than 32 bits in the result, and then we have to throw an exception. In the common case, in the fast case, the multiplication is just an x86 small instruction and a jump on overflow. It's nicely intrinsified by the CodeGen team now. So we have three optimistic operations now that may fail. The first x-getter may fail if x is not an int. Same thing with the second y-getter, and same thing for the multiplication, which if we get there, we know we have int sources, but the destination might be too wide. So we associate every optimistic operation in the AST with a program point, uniquely identifiable on the AST level. If we regenerate the method, we know what program points corresponds to which operation. The program point is actually a hidden last parameter to all these optimistic indies bound at compile time. So we always know if they should fail, if they should be too optimistic from where the error is thrown. And basically what we do after that is add an exception handler at the end of the method that catches these unwarranted optimism exceptions that are thrown if any of our type guesses are wrong. This looks messy, but I mean, you don't need to figure out too many of the details here. I just wanted to show you how it works. The catch block basically takes apart the frame state, the contents of all the local variables where any unwarranted optimism exception occurs. And since an exception, when you throw it in bytecode, it erases the stack. We have to take special heed when we generate the bytecode to make sure that all the frame state is always in local variables, and we don't have anything on the stack that hasn't been written down to local variables, or we'll lose it. In the catch block here, we actually have two cases. We have the case where there's 4 things on the frame. X can be on the frame, or we have 3 things on the frame, which is basically true through the entire method, which is the call error, this pointer, and the scope. And these reuse each other. This is provably as small code as you can require to generate these, to store these states. This is a bit sensitive because hotspot is sensitive to bytecode size. You want to keep these as small as possible. So this is potentially a weakness if you have a lot of type permutations and a lot of different states on the local frame. But in reality, we found that it pretty inlines pretty well for real-world applications. And what you do here in the catch handler is that you build something called a rewrite exception with the scope, with the frame state, with media information, and you throw it from the method to the linker. And the linker will then generate the rest of the method from where the exception was thrown. For example, if X throw the unwarranted optimism exception because it was a double and not an int, we'd have to execute everything below it with X as a double. We generate a small method stub, a slice of the method called rest of method for that. And then the next time this method is called, X will be a wider type. It will be regenerated with X as a double if that was the case, or if X were an object, X will be an object. So then we swap out code this way. So looking at the ideal Java GCD that I compile and comparing it to the ideal Nashorn, or the optimistic Nashorn GCD, we see that they're extremely similar. The only difference is we have this catch handler at the end if any optimistic assumption should go wrong, and the subtractions have been replaced by an indi to I sub, which is basically a subtraction with overflow check, which is from math sub exact, I think it is, which is an intrinsic. So these are 2 assembly instructions in the fast case instead of 1 assembly instruction. So this is pretty awesome. And the more we look at Nashorn code these days and compare it to what it would look like if it were Java, we see so many similarities. It's really cool. You can actually read this code. You couldn't read the old JavaScript code with coercions and stuff like that. And if you are right about types, you got your factor 150 before the conservative JavaScript implementation right here. We need to handle primitive types other ways as well, or types other ways as well. Local variables, I mean, X and Y came from the scope, so we could generate an indi and we could have an optimistic return value there. But in this method, liveness, we only have X and Y inside the method declared as local variables. And first of all, we do a sum, consecutive sum of all the integers from 0 to 10 to X, and then we concatenate a string to X, and then we return X, which would, I mean, it seems like a stupid thing to do, but my point here is that X is used in 2 live ranges with 2 different types. So if you want to represent X as just one bytecode local variable, it has to be an object. Otherwise, you'd have verify error if you try to do anything else to it when you concatenate that string. So conservatively, in the old world, X was one slot, and it had to be an object because of the string concatenation. So if this loop went from 0 to 10 billion, it was significantly slower for this string concatenation logic, this script runtime add that has to take place in the loop, than if we were just dealing with ints and doing an int add. So ideally, we'd like to have different types with different live ranges here. And Attila has written code, static type analysis for Nashorn that actually does that. So we both assume that we have an int up here with the optimistic typing, and we have 2 slots for X in the local variable table. It doesn't turn into an object until it needs to. And this matters a lot for methods where local variables are initiated, when variables come as locals and not from the scope. So you have to stomp out non-primitive types or 2 wide types wherever they appear. You have to do it for local variables, you have to do it for scope accesses, you have to do it for potentially overflowing operations. You have to make sure they don't store them as an object or you get boxing. You have to make sure that Java lang invoke doesn't box the stuff behind the scenes. It still does. You have to make sure that your built-in libraries don't use boxing unnecessarily. So boxing is our enemy, and the primitive types is our friend when it comes to running efficient code here. So field representation is another thing. A script object in Nashorn, which is the abstract superclass to all JavaScript objects, contains a few important fields. For instance, the property map that describes the shape of a JavaScript object, the properties it contains, things like that. the concrete subclass of script object contains a number of fields that it will use for scope variables like x and y in our application sample function I showed you. It contains a growable array called the spill pool that is also used for scope storages and a lot of other things. For example, array data that's used when you represent an object as an array or use it as an array-like object. So something like this. You have a spill pool that grows when needed in the object. And usually an object is a subclass of script object with a number of storages for scope computed in some heuristic way. For example, 4 objects here. And a property map looks something like this. You have different types of properties, the red, green, and blue, and timestamp, and they contain flags which have some JavaScript semantics, and they contain some sort of information on where is my data, which will be used to generate the method handle getter or setter to access the contents on scope or in the spill pool for this object. For example, it says use the first field, the third field, or the first index in the spill pool to find this value. And when an object shape changes, or when a property map changes, rather, property maps are always immutable and copy on write. So if you change something in a property map, you end up with a completely new property map. And for every invoke dynamic getter and setter and call that operates on a script object in Nashorn, we use a property map guard, basically checking the reference of the property map to see if it's the one that was used when we linked the call site. If it isn't, we relink the call site. This is a fairly standard way of implementing a dynamic language using Indy. So if you want to do a thing like have a scope var, you want to load the scope var from scope, you want to AND it with the integer 17, and you want to store it back to scope var. The way we look in the old Nashorn is something like this. You load the scope var with a combinator that basically does get field. It is stored as an object, as you saw. And let's assume that everything is safe and conservative. It will still be a Java lang integer in the storage slot. You queries it to int in order to soon do an AND to it, which is basically just an unboxing from Java lang integer. You execute the IAND bytecode. You got the result as an int, the primitive int on the stack. You queries it as a result, queries the result back to a Java lang integer because you need to go into the object field storage and you put field the result. And Hotspot can't remove this boxing because you're loading and storing an object. It doesn't care that you've removed, like with your nice optimistic type system and all the beautiful stuff around it. It doesn't care that you use primitives when you do the operations. If you store it back to an object it will remain and boxing will be there. So you can do several tricks here. I'll show you the ugliest thing which is currently implemented, and I'll tell you where we're going to make it more beautiful. You could do it like this, which of course is quite a waste of memory. You have an object version and a primitive version for everything in the scope. So you have a spill pool of primitives, and you have primitive fields corresponding to each object field. And it's long because a long can be used to store all the primitive types we use. Doubles can be stored as long bits. And getters and setters would know where to read, which of the fields to read, the primitive field or the object field. And the object field is an object field because it has to be GC aware in a Java object, right? We're starting to hit in the boundary, starting to want to mess around with things that the JVM didn't mean you to mess around with. So if this were your property map in the old Nashorn, we now have added a type to the properties as well, which if you change it, we'll change the property map, create a new property map, fail the guards, and relink all getters and setters because a different type is a different object shape. So what used to be like this, read the object, integer, unbox it, do the AND, box it, put it back, now looks like this. You load the scope var, which is a long, you queries it to int, L2I, for the IAND, which is like a cycle on x86. Do the IAND, queries it back, and store it in the long. And of course, I mean, this is not a final solution, but given the stuff that takes up footprint and memory, this actually took us pretty far, and it was robust and small enough not to contribute to footprint issues. There's so much else that takes up memory in Nashorn, and so this was hardly worth measuring. So right now we're using this dual field fat pointer approach, and significantly improve performance. Of course, we could think of better representation here. We're going to need some JVM magic anyway to do this better. We don't have the luxury like V8 to be able to change object layout on GCs or tag pointers or things like that. We have already, a couple of years ago, a year and a half ago, did a tagged array implementation in the sun-mist package that we discussed on the YAML list for a bit. Ricker did a very good working proof of concept, so that's probably something we want to investigate and delve down into the JVM layer for storage here. Having the entire cycle from stored scope to optimistic usage as primitive types when you have primitive types has really been very good for performance. We're basically hunting down these objects, these conservative objects, wherever we see them and remove them. And the last place to look for them is in the built-ins. The native code, as we call it, which means that it's written in Java, are the class libraries, or I shouldn't say class libraries, but built-in methods in JavaScript, like arrays and strings and regexps and whatever. They're usually very generic, have to work on everything you put in there. And one example is the array operation in JavaScript, push, which just adds an element to the end of an array and returns the length of the new array. In order to work on all kinds of crazy inputs with strings and array-like objects that aren't really arrays, etc., it turns into a lot of code. All of this was something that would just be a simple pointer bump in an array store, which makes me sad. You don't really have to see what this does. I just want you to add a slide full of codes and say, look, this is what you need for push. Be shocked. Push usually takes one argument, but it can take several, so the generic version actually takes an ellipsis of objects. If you push an int to an int array, this will box it to an object array of an element 1, which is horrible. It will turn an object to be generic, which is the length of the pushed array. It does a lot of checks to see if the array length field, you can do push to things that aren't arrays, of course, because JavaScript is horrible. And there's a lot of checks involved. And one of the things we did for 8240 Nashorn is that we added a mechanism to relink a call site. Previously, Dynalink, which we use for linking library, had switch points or guards as the ways to create an invalidation mechanism for a call site to have it relinked. We added an exception there as well, so we can now relink a call site if a certain exception is thrown, for example, class cast exception. It turns out a lot when you execute a call site in one of the JavaScript built-in libraries that you need to do check casts, you need to do various type checks to see that you're using the correct type, that it is a script object you're dealing with or whatever. And when we added the concept of relinking a site on exception, you can basically do an optimistic cast. Like in this case, this is how we access arrays for normal arrays, which are represented as Java arrays, which are basically 0 to n continuous array indexes of primitives or objects, not index 4 million or sparse arrays or string keys or anything. Normal arrays, they're all the subclass of something we call continuous array data in Nashorn. And to do an array getter now, we basically generate optimistic code that casts whatever we have to continuous array data as an optimistic guess. This is not real code. This is just method handle combinators. This is just to be human readability. And this will give you a class cast exception if it isn't a continuous array data, and we relink the call site. Before, this used to be an explicit check that took time, but we had to do that anyway. So we save a lot of time and complexity by these exception relinkages. So push, since most arrays are these continuous one-to-one map Java arrays, continuous arrays anyway, we can implement it as an optimistic method, again, like this. Basically, cast the script object's array object to continuous array data and execute push, which is that pointer bump. And this is a specialized version that works on an int and returns a long. And this is like 15 times faster. And the linker will use the same infrastructure that it does for the rest of our generated JavaScript methods to link this. There's nothing special about this. You can even have unwarranted optimism exceptions thrown from this if you have a way to roll back the methods. But most of these methods are functional in style. That means they're either completely executed, not executed at all, Or if you're halfway through, if you have a way to catch the exception, do the rest of the method manually in Java, you can fit them into the optimistic framework as well. There's plenty of candidates in the built-ins just waiting to be optimized. Array push and pop and shift and unshift and string car code at, which returns a single character string according to the JavaScript spec, but people use it as an int. I think that's the case. The number type, the math type. We convert function applies to function calls frequently because we get rid of megamorphism and specialization that way. And this, as I said, fits into the same recompilation framework used for native methods as for JavaScript methods. This is a horrible, horrible way to do object orientation in JavaScript, which I think people like Crockford really recommend. And this is fun because it makes it so hard to implement efficiently in Java, so it looks like someone has tried to do it. They have this class concept with a create key, which is a function that returns an initialize function. And all it does is to call, or a function that calls an initialize function, which is basically a constructor in your JavaScript objects with whatever arguments you give it. And then, if you want to implement something, say a color class, you take its prototype, add the fields to it as keys, add an initialize function as a constructor, and then you do a new color. It will call this initialize function, because it's in the class prototype, with the arguments boxed to an object array, sent on to as an object array to the apply. We're already megamorphic, since every different type in the world will use this creation function, so that's bad already. But we'll do this boxing to objects, and we'll do this unboxing every time. So just by turning applies into calls, if someone hasn't overwritten our apply and call, of course, which is possible in JavaScript, we can create some much better code there. We can actually create a version of this anonymous function up there that takes 3 ints, which we will when we see them at the call site, that doesn't box them, and instead of using this apply that takes an arguments array, we can pass them as an ellipsis at the end, as int, 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 generate a specialized version of the initialize function that takes 3 ints, no boxing, no arguments, no megamorphism. So that's a factor 5 to 10 on like the ray trace benchmark. And this is a common pattern. It's interesting, there's plenty of common patterns. I can talk for 45 minutes of stuff people do in JavaScript to emulate other paradigms that really sucks if you're the JavaScript engine. This is my favorite, how to play object orientation and get boxing and megamorphism with it. Other optimizations, we do partial evaluation as well. And we do it very simply, just by using the method handle constant combinator. If you have a construct like a loop from I to x.length, in JavaScript, you're not even able to tell if x is loop invariant. Even if there's references to x inside the loop and it looks like it's just red, you have no idea. Accessing x can have side effects. There's no way you can tell if anything's loop invariant just by looking at the code in JavaScript. So we opportunistically just take this x the first time we see it, when we link it, wrap it in a method handle constant, and say it's probably this x. And then we have a switch point mechanism that invalidates the x when it's overwritten. And the cool thing here is that if x is turned into a method handle constant, Hotspot will hoist it. So finally, Hotspot does something if I talk loud enough to it and present it with the correct thing. So we actually don't have to write our own loop hoisting if we present things as optimistic method handle constants. This is actually quite beneficial. It also takes away a lot of megamorphism because reading fields like undefined and reading standard functions and things like that, they're all method handle constants, so they don't need to go into anything that has to do with scope or loading things or relinking callsites. This is pretty awesome, actually, how far this got us. And there's even ripple-down effects. If you have method handle constant, you might be able to deduce that length can also be a constant. You might add receiver guards. Anyway, Hotspot is really happy when you give it method handle constants for things like this. So I turned something that couldn't be hoisted into something that could be hoisted. And then, of course, you have to invalidate it if someone overwrites it. We put NIO byte buffers in a lot of places, like the WebGL ECMA6 typed arrays, and they turned out to be a lot faster. They were represented as Java arrays before, and it's not the actual Java array representation part that was faster, but there's a lot of things like subsections of arrays and things that actually were in the NIO byte buffer API that we could use that made it faster. So Avatar were happy about that. We exported an array type for them based on byte buffers to use, and that gave them a lot of performance. We've done a lot of stuff in the JVM. Indie code tends to be branchy and full of guards and suffers a lot from type pollution. So Roland Bustrelin did significantly better type checking for optimizations, propagating types from some known points in the method. Ricker did math intrinsics, add and sub that made overflow are now intrinsified to assembly code and a jump and overflow instruction. I'm waiting for Intel to do it for me in hardware. We played a lot with the inliner. We played with partial escape analysis because even though we have removed sources of boxing in our code, I still see a lot of boxing. Java-lang invoke in the JDK has a lot of boxing in it still. And I see, as a human, places where I could remove boxing if I have partial escape analysis and boxing removal. And it's been experimented with. It sits there for a while, it goes away. We should really try to take some sort of action here to make partial escape analysis and boxing removal work better in Hotspot because there are opportunities. Rickard discovered with a simple technique, basically much more aggressively placing uncommon traps in the generated code. If you have a branch of code that's seldom taken and you replace that with an uncommon trap more aggressively than before, this turned out to be very beneficial for dynamic languages or code that assembly code from dynamic languages. Gave us 15% on the octanes on Nashorn with the optimistic type architecture with no ill effects anywhere else. So this was quite a good find. This is the best 3-line fix I've ever seen. When it comes to Java-lang invoke, we had to go through the classes and significantly beef up the implementation of the combinators. Catch exception was one example. It would always box and create objects, and was very slow. So the first tests we did with the optimistic architecture, I mean, every optimistic operation is wrapped in a try-catch combinator that rethrows the unwarranted optimism exception. No, wait, every method is wrapped in a combinator that catches the rewrite exception. So they were everywhere, and we were significantly slower than we were before with the old boxed horrible world, just because catch exception was slow. So this shows how important it is that the JDK doesn't really make up stuff like this. And I'm starting to believe that we should actually generate method handle combinators on the fly, type specialized, like we do for JavaScript methods, because you bump into so much strange stuff. Fold arguments, which I was cursing the other week, basically creates a boxed object array every time you run it, does an array copy, is like 3 or 4 wide, and then goes back to primitive types. So I think that it might be beneficial if we generated them for the call site specific types that we use them for. What? Excellent. So there's so much more I have to tell you. I could go on for an hour on optimizations and internals and stuff, but the last thing I have to tell you is that, of course, everything is not roses. The cost of all this is warm-up. We regenerate a lot of code these days when we fail to type guess, which is, I mean, it's not strange that we generate more code when we are optimistic and we fail optimistic type guesses. We have to generate a better version of the method. So the need to recompile methods has increased warm-up time a bit. There are tricks, of course. When the linker gets a rewrite exception, it contains the entire scope, JavaScript scope, so we can see more types than just the one that failed the type check are known when recompiling, so we don't need to do a lot of unnecessary, if we know another type check will fail, we'll compile it to what's in the scope already, so it won't fail. We have some heuristics. If you have a.x 10 times in a row and the first one fails, it's likely that the other ones will fail as well for the same reason. So don't compile the first one to double and leave them as ints. That's gotta be stupid. We have lazy compilation. All our compilation now is lazy at link time by default. If you have a call to GCD, you will compile a version of GCD. You will compile a version that corresponds to the runtime argument types of X and Y there. If you don't have a call to GCD, it doesn't matter that it's written there, it won't be compiled. So we're extremely lazy with all our compilation requests, and this helped. So methods only compile at demand. And if no matching signature exists at link time, we compile one as specific as possible. If a matching signature does exist, if we have an int version, we can use it. If we have a double version and we have an int call site, we try to compile an int version. And we keep these around for as much as we can. So we're slowly moving, like keeping the most efficient version of a method as we can. And code quality of lazy compilation is same as the eager compilation because we have a parse run where we establish the scope depth of symbols, which is basically the only information you need to make it as efficient as before. For reruns, we actually have solved the warm-up problem pretty well. We have a persistent code cache, and we also cache all optimistic type information to disk. So if you're running a large app with the persistent code cache on, you can, and it reaches steady state, you can basically, in AOT-like fashion, restart it and get to optimized steady state very quickly. So this works well for the second run, gives you very fast startup, but, well, not the first run, obviously. So I'm not sure what we should do there, if we should write an interpreter, or, I mean, we're playing with different things right now, so we could talk about that later. Future, just gonna finish up here. This is the WebLogic WLDF Java Flight Recorder slide, a plugin that WebLogic have written for instrumentation. You can look in Java Flight Recorder, you generate events for like database queries and SQL-y stuff and servlet, whatever. I don't know anything about these things. I just know that they've taken their application in Java and added Flight Recorder events to it that can be parsed by Java Flight Recorder. So I would like to see a JFR Nashorn button in the future with the same thing. This is uniquely, we're in the unique position that with Java Flight Recorder, we can create a JavaScript profile that no one else can do. It'll take man-years for Google to put something like this into V8, and we already have all the code. Already a Nashorn JavaScript method is bytecode with local variable tables, line numbers. It looks like Java pretty much. This fits 100% in the JFR framework already. You can use Java Mission Control to profile JavaScript by Nashorn. I use it every day. I would have been helpless this 9 months without it. But the JavaScript runtime does so much, and you can turn all these things into JFR events, and you could use them and read them in Java Flight Recorder to get like a debugger's perspective of your JavaScript application second to none. I don't see this being possible anywhere, and this actually might be something that Oracle might want to monetize. Now people are going to say, oh, evil Oracle, they'll just cache for everything. But I mean, JFR already is a commercial partly a commercial product. So for the future, I think Avatar is going to be interesting to look at where it takes us. We're already on par with Node performance there, which is cool. We'll see what the JVM takes us, the JDK, Java Lang Invoke, things like that. Nashorn, we've done the architecture. Now we've got to do the optimizations on top of the architecture to a full extent, work on warm-up problems. The hardware, will Intel give us an add exact in hardware? That'd be cool. To end this, I'm actually extremely proud. I worked 60-hour weeks together with Attila for 9 to 10 months, and we came up with a viable architecture for dynamic language performance on the JVM. We got this performance out of it in 9 very intensive months. We got to Burnoutville, both of us, but it's, I mean, this is one of the coolest years of my engineering career, actually, given the amount of impossible problems that we had to solve. So hopefully, Nashorn will be the intelligent dynamic language execution framework for the JVM, regardless of front end if you want to use it. Next week, I'm getting a thesis student, and he will start doing a TypeScript front end. I think it will be very simple for him, and we've budgeted more things during the thesis because pluggability is good. I'm over time, so that's all I had for now. Thank you so much for listening.